Okay, this video is going to focus on how we multiply vectors, and it turns out we've got three different ways that we can multiply a vector as opposed to the one way that we can multiply numbers. So first off, the first type of multiplication is if you want to multiply your vector a by any scalar, so any value that's just a number. If you multiply your vector a by this scalar, what that really means is you're multiplying each component by that scalar quantity. Right? So if you multiply your vector by 5, then each component is going to get multiplied by 5. All right, so that's our first type of multiplication, when you multiply a vector by a scalar. Now, the next two types of multiplication are when you multiply two vectors together. So I've got two vectors, a and b, and I've drawn them here. So I've got a and b, and they're separated by an angle phi. And the first type of multiplication is known as the dot product. And this is sometimes referred to, or often referred to, as the scalar product. It's referred to that because when you multiply two vectors together through the dot product, the end result is a scalar. And so that's why it's referred to as the scalar product. So the dot product is defined as a dot b is equal to the magnitude of a multiplied by the magnitude of b, and then multiplied by the cosine of the angle between the two vectors. So if we use this definition for the dot product, then that means if we look at unit vectors, so the I hat vector, if it dots into itself, well, if we look at the definition, magnitude of I hat times magnitude of I hat times the cosine of 0, well, that's giving us 1. And same thing with j hat dot j hat and k hat dot k hat. So for the dot product, anytime you dot a unit vector with itself, you get 1. Going along with that, anytime you dot a unit vector with another unit vector, you're going to get 0, and that's because the angle between the unit vectors, by definition, the angle is 90 degrees. And so for our dot product, components along the same direction, right, they'll multiply together, and you will actually get a non-zero value. For components that are orthogonal or along different axes, those will multiply together, and you'll get a 0 value for that product. So let's just look at the definition, a dot b. So here's my vector a in general, right? An x component, a y component, a z component. And then here's my vector b in general, an x component, a y component, a z component. And then I'm writing this all out, but just going to do it once. Basically, I'm going to distribute, right? I'm going to multiply this x component by all of the b components. So ax bx, ax by, ax bz. And notice I've got my unit vectors here being multiplied. So immediately I know that this is 1, this though is 0, and this is 0. Right? So those are actually going to drop out. And I'm just going to be left with this, ax bx. Remember, this is equal to 1. And so this whole thing actually just turns into this value. And then I'm going to multiply a y component by all three of those, and that's these three right here. And again, j dot j, so that is equal to 1. This is equal to 0, 0. So these three just become ay by. And then the same thing with the last three terms. I end up with this. Remember, this is equal to 1, this 0, this 0. So this whole thing just becomes that value. So when you're taking the dot product in component form, what you're really doing when you do a dot b is you're multiplying ax by bx and then adding to that ay and by plus az bz. And you'll notice there's no vector signs over here This is a scalar quantity. And you can take this definition and combine it with this definition, and we can look at the angle cosine phi, and that's just plugging in these two. A dot B, I'm plugging in here, and then the magnitude A times magnitude B, and so this is sort of the definition of the angle between two vectors. And some things to know about the dot product, that A dot B is the same thing as B dot A, and that the dot product distributes. So A dot B plus C is the same as A dot B plus A dot C. All right, so that's the dot product. All right, and our third type of multiplication for our vectors A and B is known as the cross product. And the cross product is often referred to as the vector product, and that's because the end result of A cross B is a vector. All right, so first we're going to start out with the definition of the cross product, and we're going to start with just the magnitude. So the magnitude of A cross B is equal to A, the magnitude of A, multiplied by the magnitude of B, and this time multiplied by the sine of the angle between the two vectors. And so the direction for our vector is going to come from what's known as the right-hand rule, and the right-hand rule is the idea that you start, so A cross B, you start along the, with your fingers pointed in the direction of A, and then you curl your fingers towards the direction of B, and then your thumb will point in the direction of the vector. And so in this case, my thumb, if I put my fingers in the direction of A, curl to B, my thumb would point into the page. And so the vector A cross B would point into the page in this example. So using the definition for the magnitude of the cross product, I can immediately look at my unit vectors, and this time it looks like when I do I cross I, which is magnitude of I times the sine of 0, I actually get 0 when I cross an x component with an x component, or a y component with a y component, or a z component with a z component. So this is sort of the opposite of what happens with the dot product. Now, with the cross product, if you cross I and j, well, that's the magnitude of I times the magnitude of j times the sine of 90. So the magnitude of I cross j is equal to 1. Same with I cross k, the magnitude is equal to 1. And same with j cross k, the magnitude is 1. But notice I'm just dealing with magnitudes here, and so we also have to think about direction, or whether the direction is positive or negative in whatever component, whatever direction the vector is pointing. And so what about the direction? So we are adopting a right-hand coordinate system, which means with the right-hand rule, I cross j is equal to plus k, hat direction. I cross k is the minus j hat direction, and j hat cross k hat is the plus I hat direction. Now, something interesting happens when you flip I and j. J hat cross I hat is negative k hat. K hat cross I hat, so flipping the order, is plus j hat. And then k hat cross j hat is negative I hat. So you'll notice when I switch the order, it changes the sign, right? It changes the direction. It doesn't change that the vector is still pointing along the z-axis, along the k coordinate, but it changes from positive to negative when I switch the order. All right, so we'll come back to that. So just like in the last example, I can write this all out in long form. So A cross B, vector A crossed with vector B, and I'm going to distribute all the terms, so I'm just going to point out the first three, right? So AX BX, I hat cross I hat, AX BY, I hat cross J hat, and AX BZ, I hat cross K hat. And now, remember, this term right here is 0. Anytime you cross a unit vector with itself, that is 0, so that term is 0. This term, I hat cross j hat, if we look up here, I hat cross j hat is plus k, so this term I'm going to rewrite as this, ax by in the k hat direction. Now, this I hat cross k hat right here is minus j hat, and so I'm going to rewrite this as minus ax bz j hat. And I'm going to do that for these three terms. I've got those written out here. Remember, this term is 0 because it's j hat cross j hat. And then this term, j hat cross I hat, well, that's right here. I've got to use a minus k. So this minus k hat ay bx. This term, I've got a j hat cross k hat. That's right here. So I'm going to replace that with a plus I hat. So let's see if I did that. Plus I hat ay bz. And then the same for the last three terms right here. And so after I set everything to 0 that's supposed to be 0, I'm going to group the like terms. These are both in the k hat direction, so I'm going to group them. These are both in the I hat direction, so I'm going to group them. These two are in the j hat direction, so I'm going to group them. And so I've got plus aybz minus azby in the I direction, and so that's what I've got written. For j hat, I've got plus azbx, and then I've got minus axbz, so azbx minus axbz, j hat direction. And then last, I've got plus axby minus aybx in the k hat direction, and so that's what I've got here. And so this is the component form of A cross B. So you can either work with the definition of A cross B in component form, so this, or if you happen to know the angle between the two vectors, then you can jump to using this. They're equivalent. And so this showed up when we were working with the unit vectors. It turns out that if you switch the order in a cross product, A cross B, it is not equal to B cross A. A cross B is equal to negative B cross A. So when you switch the order in a cross product, you actually introduce a negative sign. And the cross product does distribute. So A cross B plus C is A cross B plus A cross C. And that is a very brief introduction to the three different ways that we can multiply vectors.